Hello everybody and welcome back to another video. So today I'm doing something a little bit different, as you can see by the title of this, which is actually kind of a case study. So first of all, I would like to say that I am by no means a certified meteorologist. This is just things I have found myself, and this is my own explanation for this event. I didn't see much on this event, so I said, okay, maybe this is a good opportunity to get some experience really talking about some meteorology. And this is important to me because this is one of the storms that actually is the reason why I'd like to do that when I move to college next year. I like to say before this video starts that it's going to be a lot more data focused. So usually on this channel, I'll work more with just basic forecasts, but occasionally I have more data focused videos because again, this is an archive channel and I want to know how well I'm doing for the future. So this will have a lot more weather maps and data in it. So if that's not your kind of video, I will not be offended if you click off it. I'll try to explain to the best of my abilities stuff in the video, but again, it might be very meteorology focused, so just please take that in mind when you watch this. So, without further ado, let's get into it. So, this event was on June 22nd of 2015. I think I was only about 8 years old this time. This was a day after my 8th birthday, and this was Northern Illinois, so it is in my area, and this tornado was probably something I remember because I do remember hearing a lot about the damage afterward, which is a city somewhat near me. So we're talking about the Coal City EF3. This was a tornadic supercell that occurred right here in Northern Illinois. You can see all these tornado reports right here. So from this day, we have some events going on in Michigan, a bit of a wind event in the Carolinas and the Southeast, and then a few tornadic supercells that ran on through. But there's one area here you can see, which is the tornado reports right here in Northern Illinois. And that's what we'll be talking about today. So this is a little bit big there. This is the SPC's page. So this is, again, the tornado reports. Pretty active day that day, and this had been very well forecast leading up to it. So this is the day 3 severe thunderstorm outlook, and you can see here that the area of our reports that we just saw, I'm gonna move back to that tab as well. Area of our reports, which was mainly here in Northern Illinois, and here it's only a marginal risk of your weather. If we look to day 2, it's the same thing here. Wisconsin and Michigan are the main threat, with 30% hatch region up here for significant severe probabilities. I can at this time it doesn't seem like they did day 2 specific outlooks like the 4 different panels. So that would be tornado risk and all that. This is basically how the day 3 outlooks are now. If we look at the day 1 6Z outlook, so that's at 12 p.m. midnight. See 10% hatch region for tornadoes here. But this still is not in our area of interest. This is in Wisconsin and maybe a little bit in Northern Illinois, but again, nothing too interesting for that. But as the day moved on, more and more information came through, and they realized this was actually a lot more southern of a risk. So this here looks a lot more similar to what we have here. Tornado risk being here in Northern Illinois and kind of in Michigan. So it's a pretty good representation of the event. And the 20Z outlook, which is just about when storms were beginning to fire, they realized that their main area of interest would be here in Northern Illinois. They also had a 30% wind risk, mostly because this whole system looks very derecho-like, which I'll do a little crash course on in a second when we look at the real data. So these were all of our convective outlooks. They took away the significant tornado probability from earlier convective outlooks. The day 1 13Z outlook was the last one that had the significant probability, but they knew that it was going to be a pretty significant day if things did come to fruition. So we're going to look at the 500 millibar pattern just to kind of understand what was going on. Let me get a meso analysis for easier viewage. But the 500 millibar level, we had a little kinks in the flow here. You can see the contour lines. They kind of dip a little bit here, right? And there's a little bit of a trough up here, somewhere near up in Canada. We can't really see it through this product. That's what's going on. And as we get closer to the day, hold on, let me say this real quick. This is at 12Z, so this is 7 a.m. on the day of our event. So I'm gonna move forward a few steps here. You can see this trough, it kind of strengthens a little bit as it moves on into Northern Illinois. And this forcing is what really got our storms going. So in derecho events, though, which is something I talked about, the main risk with this, according to the SPC, was actually the wind risk, the 30% hatch region. The way the derechos work is often they ride along these zonal flows. So what happens is an updraft can form, somewhere here. This is for example. What will happen is all this flow moving this direction, a lot of fast flow, and it's what we call directional shear. So essentially, it's if you look at a hodograph and hodographs look something like this. If our hodograph wants to look kind of like so, right? You might see a little bit of bending in the lower levels, but directional shear is when the winds strengthen in amount as they go up higher in the atmosphere, right? We've talked about hodographs before. Essentially, each ring is stronger flow. So up here, say like 6 kilometers, we'll say this is 6 kilometers right here, and maybe this is 3 kilometers over here, right? This is our 6 kilometers, and that's be stronger than 3 kilometers, and it's stronger than the surface right here, 0. That's how directional shear works. And on this day, there was quite a bit of directional shear. If I look at the effective bulk shear here, see 60 knots, upwards of maybe in 70s and sometimes even 80 knots of effective bulk shear. Very strong winds aloft, essentially, is what was happening here, and that's why the SPC was so focused on the wind risk here associated with this trough. Again, this is 70 knots at 500 millibars, so this was looking to be a very much wind-related event. That's not really what we saw happen. We ended up seeing a bit of a shortwave move through. Look at the 700 millibar level. Oops, wrong spot there. At 700 millibars, this makes it a lot easier to see shortwave troughs. So if you move on through the day, kind of see here this little kink in the flow, these little dips in the contour lines. It's very subtle, but this is essentially what forced our storms to fire. So what I'm going to look at here actually is some data from the day of the event. So this is at 7 p.m. Davenport radar. You can see here supercells are already ongoing. We have a supercell right here. Probably supercell right here. Definitely supercell somewhere in there. It's a little bit clustered over there. Maybe a beginning supercell here, but that probably died out pretty quickly. But if we look earlier in the day, so this is about 4 p.m., which would be 21Z or 21 UTC. We can see this is when storms began to fire. Right around 22Z, 21Z. See this showery activity that fires, and that's how we get our storms to really begin. Even 23Z here as well. This is when storms really start to ramp up. And right here, this works very well with what we have in the mesoanalysis. The shortwave trough moved right through here. I'll put the shortwave trough right here. Here's our shortwave. Make the pen size a little bigger. So this is our shortwave right here. And that's forcing these little storms to fire up right here and end up moving this direction. Storms will move along the effective bulk shear lines. So if I look right here, we can see in northern Illinois, we'll move 21Z for this. So you can see that the arrow is pointing very much to this direction. That means storms will move on that direction. The thing is that the bulk shear didn't really fit with the 500 millibar flow, which was like this. So we ended up actually getting some discrete storms that would form, especially because of the forcing being very subtle. So essentially, any discrete supercells would start to move more out of the northwest in a southeasterly fashion, like so. And that is what we saw on the radar. We'll look at the radar in a bit, but right now we're looking at all the different levels of the atmosphere. I'll look at the surface level as well. So the lower isobars here indicate a surface low that was moving on through. So in the morning, we had associated with the 500 millibar trough. Right here, this is our surface low. And it's fairly strong, but it's not too strong where it forces everything up. But again, we can see here, right? If we go back a few frames, I'll delete the surface low. You can see near the Davenport area, these winds shift with the cold front. Especially this wind barb right here. I'll circle it. Pay attention to this wind barb right here. This kind of indicates the shift that was going on with the shortwave trough moving through. Pretty good change in angle right there throughout the day. And even as that trough moved in the early morning, you can see here there's a lot of forcing, a good amount of forcing to be had, but not too much where it just becomes so clustered there's just linearness everywhere. We're able to get discrete storms because of it. We can also see, a little bit of convergence right here. See how this barb is kind of like this, moving into winds, moving a little bit like this, and that could lead to a little bit of convergence right where we saw it. We can also look at the surface analysis a little bit, and it's not too indicative of anything, but we look at 21Z, you kind of see the dew points here, so I can look at this station plot. I'll try to zoom in if I can. It can be a little difficult to see. But we can look at the Illinois station plot here in Chicago. That's a 79/72 at Chicago. That's a very saturated environment. 88/77. I believe it's an 81/72. Again, this whole environment is extremely saturated at this point, and basically it's beginning to be primed for supercells. Cold front would be our main forcing. This is at 0Z, right about when storms are firing. 82/74, 88, I believe 88/76, might be a 90, 98 actually. But either way, lots of high dew points, high 70s, in fact. Very moist environment, very ready for tornadoes. I'm also going to keep moving into the CUTs now. So at 12Z in the morning of the event, let's see if we can get all these data here. We already had some morning convection going on. Hold on, let me look back at the radar soundings real quick. So we can see the radar data from that morning. MCV was moving through right here, which is, you can kind of see here, in a way, you might look at this and say that's a hurricane. There's a little eye right here. There's a few bands going on the outside of it, and it's twirling around. This is called an MCV, which is a mesoscale convective vortex. So as this moved on through in the morning, this ends up, clearing the skies and making it ready for primed destabilization, which would form supercells right there. See this little group of showers. That would die out, but with our little confluence band here, congruence, you get our little cells we saw on the radar right here on radar scope. So essentially at 0Z is when storms fired around 7 p.m. Central Time. And I can also see through this model visible satellite, which is also very useful. So we can look at visible satellite here. A little tricky, but essentially at 0Z, we can get to it. Right before we lose our sunlight, we can see these huge anvils. And we can also see these look like little tiny bits of clouds that are getting above the surface. I can try to zoom in here so you can see a little better. So here we have Illinois under there and Iowa. You can see huge swaths of clouds and these overshooting tops, which really happen with our strongest cells. I can move forward a little bit here to see it easier. This is 0Z. I believe 0Z. Yeah, 0Z here. These storms are firing right then. And very explosive, but that whole day, the MCS right here, this is our MCS, all these cloud cover, that pushes out a lot of the convection in the morning and kind of allows for some destabilization of the environment, which we'll see on these CUTs and radiosondes in a second. But as these kind of exploded, we become very strong supercells, especially that one that would move through into Coal City as well. I can also look at water vapor satellite here. It'll show much of the same. After this MCS moves through, we get updrafts to form, and you can see them just, again, explode in water vapor. This is essentially showing the same thing that we saw on the visible satellite, just at night. Huge cloud cover and huge events going on there. So if we look at our SQTs, this is the morning at ILX, so that would be Lincoln surf sounding. We can kind of see here in our hodograph here, strange hodographs. They look a little different. Not what you'd usually expect to see. Usually you'll see hodographs that favorable, like kind of like this, and that's how our supercell would form. Look something like that. That'd be our supercell shape. This one though, we kind of see, if I draw my supercell, it would kind of look like this. The more, storms that go like this, but essentially just the same, different kind of looking supercell. They'll move more in this direction. And this is kind of what we saw, and this is in the very early morning as well. If you look at the 18Z as well, something interesting we saw was kind of a cap that began to form. I'm gonna pick good colors for this. This is not a very good photograph that we saw. And I'll look at other observed soundings. So this isn't from the actual data. These are real weather balloons they sent up in the atmosphere. This is not very good for tornadoes, especially. Right here, though, we can see a little bit of a capping inversion, right? So if we look at this QT graph, we can see is that moving this direction is cooling temperatures, right? So we can kind of imagine this as an XY graph. So it's what you see in school. You might have your, parabolas kind of like this, but this is our this line here. That's our x-axis. This is our y-axis up here. Essentially, what a SQT will do is instead of having the y-axis like up and down, they kind of make it kind of like this. Still have an x-axis on some aspects, right? So these are millibars. This is our temperature lines. And what we see here is we have 20 degrees Celsius right here, 10 degrees Celsius right here, 0 degrees Celsius right there. And that's kind of how that ends up becoming a thing. So we can imagine this red line here. I'll highlight in pink just for easier seeing. This is decreasing as it goes up. Then there's just one little bit right here where this increases a little bit. This sharp increase right here. I'll undo that again. You can kind of see the red line sharply increases. We can imagine this is our x-axis moving this way a little bit instead of decreasing as you'd expect. That kind of shows a little bit of a capping inversion. And that is something that the storms had to deal with in the south, and that's part of the reason why we didn't really see too much going on there. In Davenport, you can also see this same cap here. Pretty strong here. This is the EM. This is a result of an elevated mixed layer from the southeast. So this is essentially a bunch of dry air that would get sent aloft and kind of stop storms from really happening. And look at 0Z here in Davenport. The cap is somewhat eroded, so it's not nearly as significant as it was a little bit before. So this is our cap, much stronger, a much drier region. But at 0Z, when our storms are really starting to take off here, see this a lot less of a cap, and this environment is very destabilized. 2,300 joules per kilogram. 2,400. Most unstable cape here. I mean, Sarah Hodograph is a bunch more favorable as well, right? We have that turning. We go up here. A little bit weird shape again, but same difference here. With storms moving this way, stuff will form right here. Well, another way we could tell the way these would end up looking is because of effective inflow, right? So effective inflow is at 6 kilometers, how much inflow we're really seeing into these cells. Or sorry, outflow, excuse me. So at 6 kilometers, which is right here, we only see about 20 knots of outflow versus somewhere around 40 knots of inflow, right? So if we draw a vector from the 0 kilometers here to the right mover, bunker's right mover, we see about 40 knots of effective inflow for the storm. Essentially, that means we'll get pretty big supercells versus 60 knots of effective outflow, which means that the storm won't really jet off this precipitation, leading to a pretty high precipitation kind of cell, right? So this weaker jet of 3 kilometers to 6 kilometers won't really jet off that precipitation, and this storm will keep moving into it, making these very hard to see, which we'll see in some of the products we saw and pictures we saw of the storms as well. So you look at the Lincoln data here. Lincoln, which is more in the south, there's a lot more cape that could have been had, but this capping inversion here near the surface made it so that storms didn't really form. I'm also going to use Tornado Archive for this, so we can see this is the area that our storm went through, and Coal City, this happened about 10 p.m. Central Time. The earlier supercell was about 7 p.m. Central Time. So if we look at the SB Cape and photographs, you can kind of see what these tornadoes kind of moving into. And the observed soundings didn't really do this justice. So while I don't 100% believe all the data I see here, for example, I don't think there was upwards of 8,000 joules per kilogram of cape here, we did see, these photographs did end up actually looking more like this. So useful information I found was on ustornadoes.com, which has a nice sounding for supercell that was moving through and would eventually hit Coal City and cause some damage, right? But here you can see this is our supercell with pretty strong shear in the lower levels. All right, this nice turning with height right here. You can see it's moving up, it's curving. Kind of like so, it's curving in those lower levels. But again, not much outflow, and that's part of the reason why this storm was so high precipitation when it really happened. You can also see a lot more destabilized environment, a lot more cape as well. 2600 cape here, and just absolutely no capping inversion here at all. So a very destabilized environment and a good place for all these storms to be moving into. Again, I don't trust this 6,000, 5,000 joules per kilogram, but these photographs kind of show what this storm had. And there was quite a plume of cape still up in here to be had for this storm. So, and at 3Z, it's just about when this storm had just passed through here and was passing through. There's a lot of cape here. You can see in this little mini photograph right here, in the lower levels, again, really high, but then it lacks in the higher levels, which very high precipitation was what we saw. On my little slideshow I have here, you can see the progression of these photographs. Central Illinois did not see, it saw a cap actually build in, and Davenport saw the cap kind of removed, at least mostly, for those storms to form right around 0Z. So I'm going to look a little bit now at the progression of these supercells. So essentially what we saw early on was a confluence band that would form right over here. I'll get a pause moment once it happens. But around 5 p.m., 6 p.m., moving into 7 p.m., we see this group of cells right here. And this is the one we want to look at. So if I can pause this here, right, I'll move back to 4 o'clock. In a highly sheared environment such as this, we had pretty strong inflow going in to all these updrafts. And the shear, again, we saw in the photographs, we saw quite a bit of shear in those lower levels. All that shear kind of like this. Pretty strong in lower levels, though. What that kind of means is it can kind of blow up storms as they try to form, right? And we kind of see that with some of these very discrete little showers that would rise up. Right here, this is moving. Let's look at this cell in particular. Right here, there's a little shower. Essentially, that was kind of moving into a very destabilized environment, but it didn't really have enough to punch through and form itself. What these storms need is to be in a group that kind of blocks the shear so they can form one stronger updraft that can sustain itself in the highly sheared environment. And that's what we saw with this group right here. So with these original storms, we saw a few showers right there that would form together, rise together, and end up together right here, forming a little bit of a supercell. And as the supercell matured, it would consolidate into one big updraft here, and 642 around here is already producing essentially tornadoes. So this is our velocity data. Quick little crash course on velocity. So velocity is coming from the radar. So red means it's moving away from the radar, and green means it's moving towards the radar. So what this radar sees is winds moving this way and winds moving this way. I'll use black for easier viewing here. Winds are moving this way from the radar, and winds are moving this way. You can kind of imagine this as like rotation such as this, right? So rotation, and there is a tornado most likely at this point in time. This gained a mesocyclone, which is that rotation, somewhere around 6:30, right after it crosses the Iowa, Illinois, Mississippi River border here. And these inbound winds right here, and outbound winds right here. And this is a mesocyclone. And then eventually this would keep moving, and it would strengthen and tornadogenesis, I believe, at this moment. I'm also going to look at even more products here. So this will be correlation coefficient here, which essentially shows is there debris. At that moment, we couldn't really there is a little bit of a debris ball. It's also a little bit messy here. This whole system is pretty messy, but there most likely was a tornado on the ground at this point. Now, the progression of this storm wasn't anything too special, right? It was a cyclical supercell that was able to maintain itself, mostly because of a lot of showers that kept moving into the updraft of this tornado, right? So again, right here, little shower, and these kept moving in, and this storm was very high precipitation. That is very true of this storm, right? There's a huge blob. Something people have told me they know about meteorology is the hook echo being bad. But there's very hard to see this hook echo in this storm, right? Really outline it here, it's a mess, and you might not really know where the hook echo is. In a way, it looks just like rain without velocity, knowing there's a strong tornado somewhere right in here. But our supercell is kind of embedded in the flow right here. Maybe a little bit of, more updrafts going in, but this is where our main supercell is this whole time. It's very high precipitation. This is continual, again, very moist environment, and you don't really see the hook as much and more of like a big lake. So now I'm going to look at the progression of this system. This is a few hours later, but this is just so I can see the whole progression. So this is kind of a little bit after the tornado we were seeing earlier. And we have this inbounds and outbounds. We'll mostly be using these top two figures here, the reflectivity and the velocity. But the correlation coefficient down here will show us if there's a tornado on the ground. Differential reflectivity, we're not really going to worry about too much. I mean, I could use enhanced echo tops. This would show us how strong these storms were going up, but that's not available data, so I'll just leave it like this. But with this beginning cell, this is somewhat after the last frame I showed at 7 o'clock. So this is from the KLOT radar now. So at this point, and red means moving away from the radar, and green means moving towards it. And you might see something here with a few green pixels, one right here, one right here, one right here. That's actually called folding. So essentially what happens is these winds become so strong that, at least at the time of this radar, once it hit 60 miles per hour, it folded to the other green side and would then move towards this direction again. So this will tell me exactly how strong these winds were, because right here it wouldn't make much sense to have a -50 and then a 50 like that in multiple spots, such as, like we see right here. Folding happened down here as well. Very strong inbounds and very strong outbounds right here. And we might have a debris signature there, but it's a little bit difficult to tell. If we see anything else where it's significant, we'll look at that. But as we continue this loop here, we have this, again, same thing, right? You can see the hook echo a lot easier right here. So the top left corner, reflectivity. Here's our supercell. The hook echo is a lot more pronounced in this product right here. But again, there's also all this mess all around this, right? All this showery activity right here, not part of the mesocyclone. More here. So basically, all of this just kept feeding into the supercell, and it really helped to keep it going that long. But eventually, this would end up being the hindrance and the downfall of the supercells as a whole. Keep moving on the loop here. Again, it's very high precipitation, but it was able to maintain its velocity signature as this moved on through Sublette. Produced, I believe, EF2 damage there. We can look right here as well. So, Amboy, there's a tornado on the ground at this point, a little bit south of Sublette. Somewhere down here. Yeah, it can be a little bit tricky to tell, but there is a tornado ongoing at this point. You can see also, here's a debris ball right here, and a little bit messy right here, all these winds, but you can see this is the folding once again. It's a result of the folding. So this would be somewhere around, you have to go all the way over the other side, inbound 60, and then an extra 30 moving this way. So it's 90 miles per hour inbound, and about 24 outbound. So that's about 120 miles an hour tornado right there. And this correlation coefficient is, again, what that means is stuff within here is not all rain. What red means is it's basically all the same, and that's just saying, oh, there's rain all over. This means this is different types of things in the atmosphere. This is most likely debris from this tornado. So keep moving on to the southeast. See the couplet, it kind of weakens out after Sublette. Cycles a little bit into Mendota. See this again on the damage paths here. This moved right through the city, producing some EF1 damage as well. Right around the time we're seeing 819, 826, same thing here. See the couplet right here. Most likely tornado somewhere right in here. Moves through Mendota. Same difference there. Keeps moving on to the southeast. Again, this is a very cyclical supercell. And well, really what we'd see eventually is in Coal City in an hour. I believe this produced another tornado right out here and near Wedron. I'm not sure if I can see on this map. Might be a little tricky. This would keep producing supercells. You can see up here in the reflectivity, it's just very messy as well. But really, it did continue to maintain the hook echo right here. And once again, another very strong couplet. Probably another tornado right there outside Serena. And then as we get closer to Coal City, and this is our Wedron Serena. This is Serena spot. So this is where it tightened up and formed another tornado right there. Ongoing. Might get a debris ball. Might be a debris ball there. It's a little hard to tell sometimes with the radar. Also, a fairly old product as well. This looks like it was a debris ball right there. Just a little bit, a little bit of debris in the atmosphere. This weakened out, and then this would produce our last, I think one of our last tornadoes of the day. Oh, sorry. Yeah, another one here. I didn't realize how cyclical this supercell really was. But yeah, 10 tornadoes came from this one, I believe. And as a tornado began outside of Stavanger, which I'll have to find on the radars. Well, but this would keep producing tornadoes after tornadoes as it moved south. Got lost there a little bit, but keeps producing. Very strong couplet. And then here at 929, we're approaching Coal City. So this is where our main damage swath really occurred. And we'll see tornado genesis, I think, on our next frames here. You can see right outside Coal City, we have this velocity couplet here. See as it moves on. Again, this always gets very hard to tell because this velocity is kind of moving up and down, right? It's like it's up here, and then it's down here, and it's up there, all over the place. That's how it tends to work with these cyclical supercells. As we're moving on here, you can see, in general, a more linear mode is beginning, but we still have this embedded supercell right here. Here's our embedded supercell. I'll draw a line of it. Embedded supercell, kind of like this. And it's very difficult to tell. It's very high precipitation at this point. This is where our embedded supercell is. You can kind of tell here as well because you have this weaker reflectivity here. So kind of more inflow base right there. You can kind of still see the shape of our supercell a little bit in there. But as a whole, this whole system is becoming a lot more outflow dominant. It's beginning to look more like a bow echo right here, more of a linear storm mode. And that was what was beginning to form. So this Coal City tornado happened basically right at the end. Again, there's nothing too special about the features that happened from this tornado. You can see right here, here's our couplet. Strong inbounds and outbounds are right next to each other. This would be where our tornado is. And I'll try to keep this up there as well just to see what we're looking at. Next frame is moving on to Coal City. A lot tighter of a couplet as well. 50s, 60s on both sides, about 120 miles an hour couplet. And as it moves through Coal City, see here, here's our debris ball, right? So we have all this red and then this little blue area of green and blue, essentially lower correlation coefficient and more debris in the atmosphere. You can see also a very tight couplet with both sides folding as well. I like to look at the miles per hour of this thing as we move on. 37, so I'll estimate about 40 miles per hour. So that's 80 miles per hour inbounds, 70 miles per hour outbounds, 150 miles per hour total there. That's a EF3 tornado there. And this is a 1.3 kilometers, sorry, not 1.3 kilometers, 1.3 thousand feet in the atmosphere. But that's very close to the radar, so it's kind of a pretty nice real look at this tornado. And then on the next frame, I believe that's when we get our debris ball here. So you can actually see this debris ball on the radar itself. Oops. So you can see it up here. Here's our debris ball. We used this tool earlier. Here's our debris ball here. In all spots, right? You can see it on the reflectivity especially. So again, right here, this pink. Usually pink happens with hail, but that is just simply debris being lofted from people's houses, people's homes that live right here. See, it's right where the couplet is. Debris ball shows on the correlation coefficient as well. In all these scenarios, nothing good. And I'll look at some of the damage as well after this tornado. It's kind of incredible. And so close to my own, my own place of living. That's part of the reason why this really got me into weather as well. But if you look at the debris ball to help us figure out where a tornado actually is, this is our couplet right here. So it's a little hard to delete on here. See this line right in the middle of the debris ball, and it kind of tells us how much folding is going on here, right? So 50s on the inbound side, and this is 50 miles per hour folded. That would mean about 70 miles per hour inbound winds, somewhere around 120 mile per hour outbound winds. Again, because of the folding happening here. Again, incredible how this can really work. the tornado would dissipate around Braidwood afterward, and the system was also becoming very QLCS-like. So a little bit after this, we saw a tornado genesis here in Bourbonnais. You can kind of see here a little bit of debris being lofted. See the couplet right here again. Outbound winds, inbound winds. It keeps happening with my pen here, but again, outbound, inbound here. Same thing going on. And eventually this whole system would become mainly linear after the fact. You can see a lot, again, very tight couplet here once again. That produced EF1 damage in Bourbonnais and Kankakee. But after this whole system became very linear based and would move on to produce even more wind damage after that fact as well. You can see preliminary reports, a little bit of wind damage, a little bit of hail afterward. But that was basically the end of that supercell once it became extremely outflow dominant and based on wind. So there's quite a lot of damage that was associated with this storm because EF3 damage is going to happen. TornadoTalk.com here has a very nice information about this tornado. Not a very wide path. I mean, for a tornado, for sure, right? Pretty long track for 20 plus minutes. Luckily, no one died. We did have some injuries and stuff, but no one died due to this tornado specifically, which was pretty nice. We saw 1320 yards, so that's 3,900 feet. If there's 5,200 feet in a mile, that's 3/4 wide, area of damage. That's 3/4 of a mile wide tornado. Pretty big and upwards of a wedge as well. We got information on here. You can again see the path. It's very linear. It doesn't really have occlusion. We have a radar loop as well, but that's basically what we just look at. What we're really looking for is all this damage, right? So I don't know if they have it on this website. There was a nice damage path, I believe, on this website here from the Chicago National Weather Service. You can see there were just a few spots of EF3 damage. So these orange triangles are where this EF3 damage really occurred. See a little bit right here in the southern side, a little bit here, a little bit here. This is an EF3 tornado as it went through. It had a few localized spots where it really hit hard and did some damage. And we'll see that on here. So here's our EF1 damage. Again, knocking down some dugouts like nothing, like little Jenga blocks. And EF3 damage was down here. This is a house completely wiped off foundation. Not particularly like EF5 damage, where it's completely wiped off that foundation. There's still stuff sitting here, but this house was taken off its foundation, like it says. Pushed off foundation at the bottom level, it says. So high-end EF3 damage, and that's what got this tornado the rating of EF3 with a 160 mile per hour estimated max winds. I believe that says up here somewhere. Might be in the KLOT spot, but this was estimated at 160 miles an hour tops. Yeah, you can see the 3/4 of a mile width, 16.5 miles length, and 160 miles per hour estimated peak winds. So on the ground for 27 minutes, according to this data from the Chicago Weather Service office. I can't talk too much. But yeah, you can kind of see all this damage, very severe, especially just for what wasn't really seen to be a huge tornado day. There was definitely the outlook from a few days ago, or not a few days ago, but like the outlook was out for a while, and they definitely knew there was a risk of high-end events going on here. But they did also take away that hatch risk, so kind of interesting to see that come to fruition as well. So while I was editing this video, I realized I totally forgot to show what these tornadoes actually looked like. So there weren't really many people out there chasing, at least not what I saw, especially because these are very dangerous tornadoes, high precipitation, and at night. That's not really a good combination. I was able to find 3 sources. The first one, of course, it's Reed Timmer. He's always out chasing. You can kind of see here, right? This was the environment in southeast Iowa. So this is that tornado that was tearing through before the Coal City one. So I'll look on Tornado Archive real quick. This is actually where I found a lot of my other data as well. So this is a very useful website. Highly recommend it for archive studies. But if I go to the date of our outbreak, this is most likely the tornado right here. maybe the one right here. But it essentially kind of shows you kind of the environment these tornadoes were working with, right? And you can see, no, he can't see anything here. I'll mute this so you don't have to worry about it. But crazy winds and stuff. And that's not tornado. But again, just rain everywhere, crazy winds, etc. This is another chaser. I believe his name is Chris Colora. I'll link both of these videos in the description because they're kind of cool to see what these tornadoes look like. But again, this is somewhat low resolution, but you can see the tornado here, very wedgy. Again, pretty big. And this is I believe this is the one that formed into the one that we saw in Coal City. There's also another Coal City tornado which I might even look at, but this, I believe this was the same supercell that moved right here in northern Illinois. It may have also been the one right here as well. I think Illinois City is around there. Either way, this is somewhat very similar to what these tornadoes looked like. The last one we have here is Cameron Nixon. He's very good at photographs, and I also highly recommend him as well. But we can see his view mostly with the the mothership looking supercell as well. We don't really get to see the tornado itself, but you can see this huge wall cloud. And again, it's so high precipitation. But you can see his angle as well. So this is the very beginning of the supercell, as we talked about, right when it was forming in those early cities. Those tornado warnings and all that. That's how he was able to see it. So you could, very high precipitation though. And that's the whole idea. It's in the dark, very high precipitation. But, very interesting to see. So I just want to make sure I added that as well, because I did intend to add that. I probably referenced it a few times in the video, so just to get rid of any confusion. It's also another example of, again, that subtle forcing from a little shortwave trough moving through. See it right here. I'll move to here's our shortwave trough moving through, and that was what forces our supercell to move like so. So it's an interesting supercell that I'm glad I've really looked at. If you have any questions, let me know. But I think that's gonna be the end of this case study. I don't really want to do too many of these, but this is definitely a tornado that, again, sits very important with me. So if there's any questions on this event, please let me know in the comments. But thank you for watching, and I will see you next time.